when you're copying this down, a few little things to pay attention to. There's a time interval being expressed here. Make sure that in your diagram you too have recognized that there's a time interval here. When you're drawing this, make sure you see where the graph starts and where it ends during that time interval. Pay attention to what's on each axis so you understand what it is this is showing you. Mm-hmm.
Is the 15 still on the y-axis?
Yeah, it's supposed to be. It's just kind of moved over a little bit, I guess. So. And hopefully, you guys should be able to write me a sentence describing what this thing might be doing. If this were on a quiz, I would ask the following couple of questions about it. Is this object traveling towards or away from the origin? Is the object speeding up or slowing down? Those are the simple questions, but they're not always going to look like this. I'm starting with as easy an example as I possibly can. Now, I'm going to add some vocabulary today. This vocabulary is not particularly complicated, but it's the kind of vocabulary we're going to use for something known as Galileo's rules. Already kind of been working on this, but not been using a name for it. This is also known as uniform accelerated motion. They mean the same thing. Now, this object has a clear velocity at the start of the interval. The fact that it might be 0 isn't as important as what we're going to name this. The velocity at the start of the interval is called the initial velocity. And we're going to start transitioning into using symbols rather than using graphs. So the symbol we're going to use here is a V with a subscript I next to it. And we'll be using subscripts quite a bit. Technically, because velocity is a vector quantity, I'm supposed to put a bar on top of it as a way of alerting you to the fact that V is a vector quantity. Now, I will forget to do that, and you won't be penalized if you forget to do that. But it is implied that you guys will remember that velocities are a vector, so that this value should always be given to me if I'm asking for it, with the direction. Moving forwards and moving backwards will be fine, positive or negative if necessary. The velocity at the end of an interval, this is going to be a little bit disappointing for some of you, but we call this the final velocity, but that's a little bit misleading because the object could keep going. We say final because it's the final velocity for the interval that we're watching. So we have to be careful here when we use the word final velocity. It might it might continue to move after this. We don't really know. We're focused on this idea that there is a time interval involved. So we are observing only 5 seconds of the object's motion. So for time interval, we're just going to use a t. It is not a vector quantity, so it doesn't get the bar on top. Now, we've talked about this now for a couple of days. This area underneath the curve has meaning, and we've talked a little bit about that meaning. We call this the displacement. displacement is change in position and is also a vector quantity. So in order to find symbology that matches that definition, we use the delta symbol. And I know you've learned what the delta symbol is in the other class, so delta means change in. And if you've not been taught that, it's okay. You're going to be taught it right now. The delta symbol is a triangle. It's a Greek letter. And we're going to say delta x to mean the change in position, or the change in x, where x represents position. And it is also a vector quantity. Now, if you're unfamiliar with some of this symbology, it's okay. Position is a vector quantity, and we use x to represent position. So displacement and position are different things. The delta makes a difference here. Technically, if you've never used delta before, it would be listed as x final minus x initial. That's technically what the delta tells you to do, change in. You would have used it probably in algebra to say delta y over delta x. But it has a more far-reaching meaning. So the delta symbol itself just means change in. I will probably just refer to it as delta x. If that's okay with all of you, if that confuses you, I'll try and remember to say the word change in x. So these represent 4 of the motion variables. There's actually a total of 5 motion variables, but these are the 4 that we have so far. And I'm just kind of explicitly defining them. They're words we've already been using. Now, it shouldn't be too big a deal for me to ask you to figure out what the displacement of this object was. You know how to do that. You can find areas. I feel pretty confident that that's not asking too much of you. But we also, at the end of class on Thursday, talked about something else here. And since I was inconsistent between first and second period, I want to really emphasize this. This object's velocity is changing the whole time. And we refer to the change in velocity as the acceleration. If that wasn't expressly discussed in class, let's discuss it now. Acceleration is the change in velocity. It comes from looking at the slope of this line. And that's kind of where we left it on Thursday. The unit of the slope was meters per second per second. Remember we talked about trying to figure out what the meaning of slope and area is. This unit is what you get when you look at the units on the vertical axis divided by the units on the horizontal axis. And this is a complex unit, but it states the definition that I want you to know. If you look at the unit, it tells you that we're looking at how much the velocity changes over time. Anytime there's seconds in the denominator of any fraction, that fraction is a rate, R-A-T-E, a rate. And it tells you how fast something changes. That's what rates do. Interest rates are the same kind of thing, they just do it with money. So anything that's called a rate has seconds in the denominator. Acceleration, by definition, is the rate at which the velocity changes. The rate at which the velocity changes. We will define that as the acceleration. And it's the slope of this line, which, if you were to do the math on it, is 3. But the units, meters per second per second. I'm going to say them out like that all the time, but some of you will realize this could be written as meters per second squared, and that's fine too. I'm going to keep saying them meters per second because I want to encourage you to think about what it means. This object has a slope of 5. I'm sorry, a slope of 3. Positive 3. Which means that the velocity is becoming more positive. That may or may not tell you whether this object is speeding up or slowing down. The word acceleration has a different meaning in your history than it does in this class. We will not use the word decelerate in this class. In fact, don't write it on anything that you turn in for a test or a quiz. You may wish to emphasize that in your notes, that the word deceleration doesn't have meaning in this class. It's not the opposite of acceleration. Decelerate is a colloquial term that you mean slow down. But the word accelerate includes speeding up and slowing down. It is any change in velocity, both to increase speed and decrease speed. So anytime something slows down, it is also accelerating. So be careful. Don't use the word decelerate on a test. If something's slowing down, it is still accelerating. And don't expect the word accelerate to mean speeding up. You have to be able to figure out whether something is speeding up or slowing down due to the context. This one I've given as an example is pretty easy. This object is speeding up. And that's pretty easy to figure out how, because it started at rest and after a while it's going 15 meters per second. That's clearly speeding up. Yes, sir?
If an object is quote unquote decelerating, would the acceleration for the actual unit for whatever you say it's accelerating, would it be like -5 meters per second?
Well, let me try providing you with two examples to show you why we have to be careful about the word decelerate. Is that okay?
Yeah.
All right, so this was supposed to be a quick exercise in symbology. Have we successfully done that? You guys have the symbols that go along with everything? What do you think we're going to use for acceleration? Is the A work okay for all of you? Because that's pretty straightforward. A with the bar on it, because it's a vector quantity too. So these 5 things represent the symbols that we're going to use to describe motion. Now, part of what I have to get you to be able to do is be able to make predictions, solve problems based on what we see about the motion of an object. And for the time being, what that really ultimately means is that we are going to establish that there are 5 motion variables, and the motion of an object should be able to be described by identifying all 5 of the pieces of information that should be given. They may not all be given, but in any problem, you should try and identify what has been given to you. For example, in this problem, we've been told that the time interval is 5 seconds. It's a piece of information that was given. I can read it right off the graph. We're told that the initial velocity is 0. Again, a piece of information that was given. I can read it right off the graph. And we know that at the end of the interval, the object's traveling 15 meters per second. All pieces of information that have been given to us by just looking at the graph. But we've actually been given more information than that. From the graph itself, we can look at the slope and figure out what the acceleration is. Now, most of you can do slope. You understand what slope is and how to do it because you've done it before. But think technically about what you're doing when you try and figure out the slope. It's the change in the y, so it's y final minus y initial, divided by the change in the x, which is going to be x final minus x initial. This is what you guys were given when you were in like not elementary school, but middle school for doing slope. Does that sound familiar to you? Mm-hmm. On our horizontal axis, we have time. You could say time final minus time initial if you want. And on the top axis, we have velocity. V final minus V initial. This is how we figure out the slope. But the slope is acceleration. I'm bringing this up because this is actually a formula for figuring out acceleration. So even if I don't have a graph, if I have the initial and final velocity and I have the time interval, I could probably estimate what the acceleration is without having to put it on a graph and then find the slope. In fact, I'm going to probably reduce the bottom to just t, since our intervals tend to be starting from 0. At the same time, I can also figure out the displacement. We know that that's the area. 1/2 base times height. But the height is the final velocity, and the base is the time. And this would give me the displacement. This is another formula. I don't necessarily need to have a graph to figure out what the displacement is.
Do you need a line over the x and the displacement?
I don't usually put them into formulas that way.
Okay.
I think it's cumbersome enough. Now, I should be able to ask you without having much difficulty how far the object traveled, what its acceleration was from something like this. But this one's not so terrible. It's when we look at something a little more complicated that this is going to get harder. So, how many of you feel pretty confident that this is making sense so far? Not a problem? All right. So I'm going to change things up and maybe help create some confusion, if that's okay. This is not my intent for you to be confused. It's to make sure that we've covered possible cases. All right, so can you how many of these 5 things can you figure out from what's here? Take a moment and see how many of them you could perhaps figure out just by looking at the graph or working through the things we've talked about the last couple days. All right, let's go ahead and get started here. So there are 5 motion variables. I've listed them already here, but they are the displacement, which is a vector. You should give me direction when you give me your answer. Final velocity, initial velocity, again, you should give me direction. Those are both vectors. Acceleration, also a vector, and time. So let me see. Kayla, can you give me any of these? The final velocity is 8. Is it positive or negative? Positive. So when asked in class for something like this, like on a test, I will be looking for the following things in your answer. Did you give me the number part? Did you give me the unit? And did you tell me the direction? All of those have to be there to get the correct answer. So, let's see. Luca, can you give me another piece of information? Delta x is positive 20 meters. Did you get that by finding the area? Excellent. Does anybody need help with that? I'm thinking this is 8, this is 2, that's 10. 1/2 of 10 is 5, and this is 4. 5 times 4 is 20. So, moving right along, let's go to, I don't know, another table. Victoria, can you give me a piece of information?
The initial velocity is 2 meters per second, positive 2 meters per second.
Excellent. Excellent. Bianca, can you give me a piece of information?
The time is 4 seconds.
Time is 4 seconds. Excellent. And Nicole, can you give me a piece of information?
I originally thought that A was 20. Like 20 meters, I thought that was the area.
That's okay. It's the slope. So Can we do the slope together?
Yeah.
Sure. We start here at 8,
Mhm.
and we subtract 2. What do you get?
6,
And then that's 6 over 4.
which is
3 halves, yeah. So it's a vector, so I'm going to say positive because the slope is positive. It's 3 halves, and our units are meters per second per second. Now you could put meters per second squared, and that would be just fine too. I'm going to write it as a complex unit for the next week, just so that we get used to seeing that it's a rate. But if you want to write meters per second squared, that's perfectly fine. 1.5 would have been just as well here, if you did that. Those are the 5 motion variables, and we got them by taking a look at the material that was given. I want to transition us a bit, if I could. You guys are going to have to recognize that the reason I've been doing it this way is to help us move towards a set of symbols to express these things rather than graphs. So when I say that the acceleration is the slope, I want to remind you that that means the slope is the change in the y variable divided by the change in the x variable. All right, the change in the vertical divided by the change in the horizontal. But our vertical on this graph were velocities, and our horizontal on this graph is time. If we want, we can express the acceleration in the other symbols that we have. It shouldn't be a stretch that we can also do that for displacement. Look at the symbols that we had to use here. The initial base is actually the starting velocity, the initial velocity. That second base is the final velocity. And the height is really just the time. I know you're finding area, but recognize that those bases are just velocities. Now, I want to really play with this a bit, but I need you to see something. In our first example that we just did, would you agree that the object was speeding up? So, I'd like you to take a look at this one. This should take you less than 60 seconds because I didn't change any numbers. Flesh out the motion variables again. You shouldn't have to calculate very much, but I need to make a point. Now, generally calling on you personally heightens your level of concern. So I hope your level of concern is heightened enough because I want to call out a bunch of people real fast. So make sure you've talked it out real quick with the person next to you. Have all these 5 things ready to go. We ready? All right, West, give me the velocities.
The initial would be 8 meters per second, and the final would be 2 meters per second.
They're both positive though, right?
Yes.
Excellent, excellent. And let's see, Marco, can you give me what the time was?
That's 4 seconds.
4 seconds. Good, good. All right, so we got the low-hanging fruit there. Tara, can you give me either the displacement or the acceleration? Right, we still moved 20 meters. But the area is the same, so this object went the same displacement as before. So that shouldn't be a huge surprise. Lauren, can you give me the acceleration?
Would that be -3/2 meters per second?
meters per second squared or meters per second, yes. I'm gonna put negative 1.5, that's all right. It's negative. The big takeaway here is, the only difference, this object started fast and slowed down. That makes sense too? Now, you might begin to develop the idea that if the acceleration is positive, the object is speeding up, and if the acceleration is negative, the object is slowing down. And you'd be incorrect. You need to pay attention closely here. Do it again. All the numbers are the same. This isn't about the numbers. It's about having you see something. Are you seeing it? Is this slope positive or negative? Sure is. It's got to be negative 1.5 meters per second per second. Initial velocity, positive or negative? Negative 2 meters per second. Final velocity, positive or negative? Negative 8 meters per second. Still 4 seconds. Displacement, negative 20, because the area is on the bottom. This object speeding up or slowing down?
On the last graph, why wasn't the displacement negative?
On the last graph, why wasn't displacement negative? Because the area was on the positive side of the graph. And on this one, the area is on the negative side of the graph. Okay, so first, this is a negative displacement. This object moved behind us. This could be you sitting in the middle of the street, and instead of putting it drive, you put it in reverse and floored it. You would be going faster, right? Your speed would be increasing, but you're going backwards. Negative or positive acceleration does not tell you if you're speeding up or slowing down. But I will try to get you to say it does. You can't tell whether you're speeding up or slowing down just from the acceleration. You can't. You can't tell if you're speeding up or slowing down just from the acceleration. You need to know the velocity. Now, you guys like hard rules. Here's a hard rule. If the acceleration is in the direction of the velocity, you're speeding up. If the acceleration is against the direction of the velocity, you're slowing down. I'll say it again. If the acceleration is in the direction of the velocity, you're speeding up. So if they're both positive, you're speeding up. If they're both negative, you're speeding up. But if the acceleration is against the direction of the velocity, you're slowing down. So if the acceleration is positive but the velocity is negative, you're slowing down. I don't need to give you every possible combination, but if the velocity and acceleration are opposite signs, you're slowing down. That's an oversimplification, but it'll help you a lot in the beginning here. You will need to be able to tell me whether the object speeds up or slows down. You do it from the graph too. Now, there's more to this than what we just covered here today, because I also need you to take a look at, say, this graph and be able to draw what the position graph would look like from this. If you can't sketch it, we have a problem. So would you be so kind as to try and sketch it in our closing minutes? We have 5 minutes.
Try to sketch the position graph.
What's that?
Try to sketch the position.
I couldn't hear you.
Try to sketch the position.
Yes, I would like you to try and sketch the position graph. I'm going to say some things out loud in hopes of helping you. The first thing is make sure the intervals match up. You don't know where the object starts. So start your object at the origin. You know the area was 20 meters. So you know how far the object moved. Meaning you know where the object is after 4 seconds. Mark that on the graph. Now, here's where you're going to have trouble. You have to connect these two dots together. In our prior examples, you just connected them with a straight line. That made sense because the velocity was constant, but is the velocity constant here? In your notes, a big reminder here is that the velocity is the slope of the position graph. So our slope is changing. The slope of the position graph isn't constant, it's changing. So start with one dot and one dot only. I'm going to start with this one down here in the bottom. What is the slope at time 0? It's 8. That's the slope. It's positive 8. Now I know what positive 8 looks like, but it's positive, and it's 8, so it's steep. Yes?
So what do you just come up with a curve wall?
I don't know yet. What I'm going to do is I'm going to put like a partial slope at each of the dots, and I'm going to see what it tells me to do. For example, at t equals 4 seconds, the slope is 2. I don't really know what 2 looks like, but I know 2 has to be shallower than 8. So I'm going to make a partial slope that's shallower. Mark a little partial slope on each of the dots. Now you have to connect them with some kind of smooth transition. Because there was no breaks in this graph, there could be no breaks in our graph here. So what smooth transition will likely connect them? I'm thinking some kind of curvy line. Like so. The partial slopes should tell you the concavity of your graph. If you don't know what that phrase means, concave down and concave up, then you're about to learn probably in pre-cal. If this were me and I wanted to be prepared for tomorrow, there are 2 things you should do. First, I've posted a worksheet that has practice about finding displacement and acceleration, the displacement and acceleration from graphs. The first 3 are easy. They're just what we did here. The next 3 are hard. Don't do them yet. But also, you have 2 other graphs here. All the same information, but you should see what their position graphs should look like. Tomorrow, that should be the first thing we do, is check your practice position graphs against what I'll have here. I'll have them all on the board so you can compare them. Does that make sense? All right. And that is it for today.